Fine. So now let's talk about the preparation from carboxylic acid. When we talk about the preparation from carboxylic acid, here we talk about a very important and a simple reaction. Now this reaction has a very big name. It is Hill Volhard Zielinski reaction. Now, by name it appears to be a devil, and by short form it appears to be like a virus. But the reaction is too simple. The reaction is simply that we have a carboxylic acid having at least one alpha hydrogen, and we react it with X2 in presence of phosphorus. Okay. Now this X2 in presence of phosphorus, this is capable. Okay, we can have Br2, we can have Cl2 here. We prefer to have Br2 here because chlorine being more reactive, once it has consumed one alpha hydrogen, two alpha hydrogen, three alpha hydrogen, it can go on further into the chain again. That's the problem with chlorine. Bromine, after it has consumed the alpha hydrogen, it's going to stop. It's not going to go beyond. So here it gives us the halogen COOH. So it gives us a alpha halo acid. Okay, so that's what we have, one reaction, a simple one, carboxylic acid to alkyl halide. Now we have something called borodine Hunsdaecker reaction. In this borodine Hunsdaecker reaction, we again have a carboxylic acid, RCOOH. We react it with Tollens reagent. Tollens reagent is ammoniacal silver nitrate solution. Tollens reagent. This is ammoniacal silver nitrate solution. By the formula, we can write it as Ag NH3 whole twice NO3. This is what we have as ammoniacal silver nitrate solution. It's a complex. Now when it reacts with our carboxylic acid, it gives us RCOOAg. Clear? Now this RCOOAg is reacted with Cl2 or Br2, and again we prefer Br2 because of its less reactivity, to give us RBr plus CO2 plus AgBr. Okay, so here we are able to get an alkyl halide having one carbon less than the carboxylic acid. So again, it is a step down or degradation reaction. Yeah. Is that clear? Hello? Okay. So it is a step down or degradation reaction. That's what we talk about, the borodine Hunsdaecker reaction. Now then we have a reaction. Now it's an offshoot of this reaction. This is called the Birnbaum-Simonini. Yeah. Offshoot means that the reaction goes in the same manner, but it gives a different product. Or you may say a little bit of extension. Okay. Now here again we have the silver carboxylate. And instead of Br2, we are using I2. Again, it's going to react. It's going to give us Ri along with CO2 along with AgI. That's a simple thing. The only thing is that Ri is extremely reactive. The carbon iodine bond is extremely weak, And that is why this Ri, which is formed in the first step, has a capacity to react further with a silver carboxylate, and it forms RCOOR along with AgI. So in this case, the final product, rather than being an alkyl halide, it turns out to be an ester. So that is what we have as Birnbaum-Simonini reaction. So this was the method of preparation of alkyl halides from carboxylic acid. Okay. Now alkyl halides are not prepared from the carboxylic acid derivative, that is esters and hydrides and all, and not they are not prepared from that. Now we are going to talk about the preparation of aryl halides. Okay, so we have the preparation of aryl halides. When we talk about the preparation of aryl halides, there are certain very simple methods which you have done in 11th class as well. Let's say we have benzene ring, and we react the benzene ring with X2 in presence of Lewis acid. Now this Lewis acid could be most famously AlCl3, it could be FeCl3, it could be FeBr3, it could be Fe plus Br2. Okay, now all of these, Fe plus Br2 is actually going to react, iron is going to react with bromine and form the ferric bromide right in the reaction mixture, which is going to act as a Lewis acid, and then Br3 is going to react with bromine and do the bromination. Okay, so here, is it now clear? Okay, I think there is some net connection problem. Okay, so this is what we have as FeBr3. So these are all Lewis acid, and what we get here is the halobenzene along with HX. Have you done the mechanism of this reaction? Have you done the mechanism of this reaction? The halogenation of benzene, or in fact electrophilic substitution reaction of benzene. Okay, I'll start with the mechanism. If you remember, fine enough, or we are going to complete it. Okay. Okay, so we have XX. See, whichever reaction we have not done, we are going to do right where it comes for the first mention, because we don't know when we are going to have the next mention. Okay, so we have XX, and we have a Lewis acid, most often let's say AlCl3. This AlCl3 is going to attract the electron cloud of the halogen. The halogen is going to further attract the electron cloud of the other halogen. What we are going to get is X plus along with X AlCl3 with a minus charge. Now this X plus is an electrophile. Okay, benzene ring is an electron rich species. Here we have the benzene ring, and it has hydrogens along with it. Okay, now it is having X plus. So this bond shifts over to the halogen. It breaks. Now here it is H, here it becomes X, here we have the positive charge, and we have the hydrogen also here. We have the hydrogen, 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 hydrogen. Here we have the bond, here we have the bond. Now, there are two possibilities. Either a nucleophile can attack on the positive charge. If the nucleophile attacks on the positive charge, then in that case, this double bond is going to be broken. It is going to be an electrophilic addition reaction. Okay. Or the second thing what can happen is that this hydrogen bond breaks apart. In that case, the aromaticity of benzene is going to be restored. What actually happens is that this bond breaks apart. The hydrogen moves out, and we get the product as halogen here, the bond here, the bond here, the bond here. So it is haloarine. Clear? Now this method can be used for the preparation of chlorobenzene. It can be used for bromobenzene. Clear? It can not be used for fluorobenzene. Okay? Fluorine is extremely reactive. It is if it gets a chance even to touch a hydrocarbon, any hydrocarbon, it's going to explode. So yes, explode means explode. Okay? It's extremely reactive. So fluorobenzene cannot be prepared by this method. If we want to prepare iodobenzene, then there needs to be a little modification. And that little modification is that when we use iodine, the HI formed as a product is a very good reducing agent. Being a very good reducing agent, it reverses the reaction. That means we again end up with a benzene and iodine. We are not able to get iodobenzene effectively. So what we need to do is, we need to use some oxidizing agent, which could be HiO3, or it could be HNO3, which is going to oxidize the HI which is formed in this reaction and prevent the reverse reaction. So that is what we get. If we use an oxidizing agent here, we are able to get iodobenzene. So preparing iodobenzene is in presence of oxidizing agent. Is it clear? Clear? Now we need to understand very simple thing. Let us say we have a benzene ring along with CH3, that is toluene. If I use Br2 in presence of light, or I use NBS, then the product that I am going to get is CH2Br. It's going to be a radical substitution reaction. Clear? And if I am going to use Br2 in presence of a Lewis acid, if I am going to use Br2 in presence of a Lewis acid, then in that case the reaction changes and we are going to get a mixture of ortho and para bromotoluene. Is it clear? Could you give me the IUPAC name of these two compounds? This. Okay, fine. 1 bromo, 2 methyl. No, 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 no. Don't use ortho. Don't use ortho. It is 1 bromo, 2 methyl benzene. The other name, if you wish, that would be 2 bromo toluene. Okay. Now this particular compound, you can term it as 1 bromo 4 methyl toluene or benzene, or you can use it as 4 bromo toluene. Is it okay? So you need to understand that this was a question in IIT advanced exam. The naming, yes, naming. 2017, IIT Advanced. Both the names were given. Both the names were given. And it was a multiple correct question. And this multiple correct question was asked in IIT Advanced and it is given in NCERT. That's the important thing. So that is the preparation of the aryl halides from benzene. Is it clear? Now, one thing more you need to understand that if we use benzene and we react it with Cl2 in presence of light, then in that case, rather than having a free radical substitution or having a electrophilic substitution, we end up with a free radical addition reaction. And that free radical addition reaction is going to have this kind of a structure. What would be the name of this compound? The formula is C6H6Cl6. In short, it is called 666. It has another name also. It is called gamexene. It is also called lindane. You need to remember, you will have to give the number. 1, 2, 3, 4, 5, 6. Hexachlorocyclohexane. Is it okay? Yes. The common name is benzene hexachloride. Although it doesn't contain a benzene ring, but this is the common name, so it is also called BHC. That's an excellent pesticide. Yes, gamexene, lindane, benzene hexachloride, BHC, 666. That's all the name of this particular compound. So this is what we have as a free radical addition reaction. Okay. Now, once we have talked about the free radical addition reaction, this is what we have preparation of alkyl halides from a benzene. Now we are going to talk about another method of preparation of alkyl halides. And this method is going to be from aniline. Yes, aniline. Now the reaction which we are talking about, if aniline is treated with NaNO2 in presence of HCl, then we get a compound which is N2 plus Cl minus. This compound is called benzene diazonium chloride. Okay. Now this is called diazonium ion or diazonium salt. Now if this diazonium salt is treated with something like CuCN in presence of HCl, it gives us the compound CN. This is benzonitrile. Okay. Now if this particular compound is treated with CuCl in presence of HCl, then we get chlorobenzene. If it's treated with CuBr in presence of HBr, we get bromobenzene. Okay. Now these reactions are called Sandmeyer's reactions. Okay. I generally call it is in sand, mitti mein. Okay. But then another scientist, he said that why do we need to add CuBr or CuCl? Why can't we simply have Cu along with HCl? The Cu is going to react with HCl and is going to produce the catalytic amount of CuCl in the reaction mixture itself. Now, when it does so, it's going to form again Cl. Then we can even use Cu along with HBr, and it's going to give us Br. Now it goes a little higher as compared to sand. Instead of mitti, it goes into gutter. It becomes gutter mein. Okay, these are Gattermann's reactions. Then, if we want to produce iodobenzene, we don't need to do a lot of things with it. We simply put Ki and we end up with iodobenzene. Okay. Now, there is a very specific reaction. We take aniline. Okay. This aniline is made to react with NaNO2 in presence of HCl, wherein it gives the benzene diazonium ion and salt. Now this benzene diazonium salt is made to react with HbF4. This is tetrafluoroboric acid. Okay. When it reacts with HbF4, we end up with benzene diazonium fluoroborate. If this benzene diazonium fluoroborate is heated, it undergoes decomposition. It gives us fluorobenzene along with BF3 along with N2. Now this reaction has a name. It is called Bals-Schiemann reaction. Excuse me. This is called Bals-Schiemann reaction. Okay. Now this reaction is the only reaction to prepare fluorobenzene. So there isn't any other method to prepare fluorobenzene. Clear? So with that, we have just finished off with the methods of preparation of alkyl and aryl halides. Okay. Now we are going to, yes? Can you hear? Yeah, is it working? Okay. So that's what we have as the Bals-Schiemann reaction. That is what we have as the methods of preparation of alkyl and aryl halides. Now we are going to talk about their physical and chemical properties. Okay. First of all, we are going to talk about the physical properties. When we talk about the physical properties are melting point, boiling point, solubility, and density. Okay. So first of all, we talk about something called the melting point and boiling point. Clear? I think we had already discussed about the trend of the melting and the boiling point of the various compounds of the organic compounds. Okay, that is the melting and the boiling point is decided by the various forces which are going to act between the molecules. In the case of organic compound, all are molecular compounds, and that is why the melting and the boiling point is going to depend on the weak van der Waals forces, that is the surface area, the dipole-dipole interaction, and lastly but not least, the hydrogen bonding. Okay. Hello? 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 Sushin, are you there? Hello? Okay. So, when we are talking about the melting point and boiling point of the alkyl halides, talking about the melting and the boiling points of alkyl halides, in this case, when we talk about the interparticle forces, these are just the weak van der Waals forces, which are depending on the surface area. So as the surface area is going to increase, the weak van der Waals forces are going to increase, and with that, the melting and the boiling point is going to increase. Okay? So in fact, we are going to have CH3F less than CH3Cl less than CH3Br less than CH3I. Okay? Similarly, CH4 would be less than CH3Cl, would be less than CH2Cl2, would be less than CHCl3, which is going to be less than CCl4. Is it okay? Similarly, if we have CHCl3, it's a liquid. CHBr3 is kind of a semi-solid, whereas CHI3 is a yellow colored solid. and that is why we use it as iodoform test. Okay, so that's what we have as a melting and the boiling point trends. Now these all alkyl halides, whatever they may be, they are insoluble in water, or you may say their solubility is so low that it's practically insoluble. Is that clear? So that's what we have as the solubility of alkyl halides. Now, now there is a very important concept, and that concept is what we call as the dipole moment. Okay, we talk about something called the dipole moment. Now, dipole moment has two factors. This mu is equal to the charge separation, magnitude of charge separation, into the dipole moment vector. Okay, now if this is the case, most often we talk about the charge separation only. We only talk about the electronegativity difference. But when we talk about the alkyl halide, this is a peculiar case where not only we need to talk about the electronegativity difference, we also need to talk about the bond length. And what we find is, if we talk about something like HF, HCl, HBr, HI, then we say that HF has the maximum dipole moment and HI would be having the least. But in the case of alkyl halide, and this trend you need to remember, CH3Cl has the highest dipole moment, followed by CH3F, followed by CH3Br, and CH3I. Is this clear? Yeah. This particular concept you have to remember. Clear? Yeah, there is a reason. But the reason is something like we know the observation. That is how we create a reason. Because here there are two factors. This is what we have as charge separation. This is what we have as bond length. In all the other cases, it is the charge separation which dominates. But this is a peculiar position where the bond length is dominating. So we are giving the reason by the observation. So you cannot predict the observation by creating a reason. Is that clear? So that is why we can't remember. We cannot understand it. We have to remember it. Is it clear? Now let's talk about something called density. Now when we talk about, yes. So what are we going to talk about the density on what factor? Okay, perfect. In the gaseous state, it's going to be just the molar mass. Yeah, what's that? Perfect. We termed it as average atomic mass. Okay, so whichever one has the average atomic mass higher, that is going to have a higher density. Let's talk about CH3I, CH3CH2, CH3CH2I, and we have CH3, CH2, CH2I. Which of these is going to have the highest density in the liquid state or solid state? 127. Bus, fine. This has the highest, this has the least. As the carbon chain length increases, the density decreases because the average atomic mass decreases. Okay? So now we have just talked about the reactions, the physical properties. Okay. Now we are going to talk about the reactions of alkyl halides. Okay. There are various reactions of alkyl halides. Okay. They are capable of showing almost all the reactions. Okay. Now the very first reaction that we are going to talk about is the reaction of alkyl halides with metals. Okay, clear? Let us say we have an alkyl halide Rx and we react it with a metal. For example, we react it with sodium. Okay. Now sodium is a radical. It contains an unpaired electron. Now the sodium is able to donate the unpaired electron to the halogen. And then the halogen is going to also give its electron right here, break the bond with carbon. And then it's going to give us R with a radical along with NaX. Okay. Now this R radical can further react with another sodium atom to give RNa. Now this R minus Na is much electropositive. Na is going to have a positive charge. R is going to have a negative charge. So this is R minus. Okay. Now this R minus is highly unstable. Sodium plus is stable, but R minus is highly unstable. The carbon does not want a negative charge with it. So it searches for a positive in the system. Now the other positive that this R minus is going to get is going to be another molecule of alkyl halide. Because this particular carbon has a positive charge and this halogen has a negative charge. Halogen is more electronegative. And that is why the electron pair of this carbon is going to attack on this particular carbon, break the bond, and we are going to end up with something like R with an R along with NaX. If I just add all these reactions, I am going to get twice of Rx plus twice of Na gives us RR plus twice of NaX. Any confusions here? What's the name of this reaction? A very famous reaction. Maybe you have done it like this. You have done it like this. Name, name. You call it sometimes Wurtz coupling reaction. Now, this is the preparation of an alkane from alkyl halide. Okay, this is the Wurtz coupling reaction. Now, when we talk about the Wurtz coupling reaction, the Wurtz coupling reaction has certain limitations. The first limitation is it can't be prepared to prepare methane. Okay. Second limitation is that if I use two alkyl halides, then it's going to give me a mixture of alkanes. Okay. So any alkane which actually requires two different alkyl halide to be used can't be prepared using Wurtz reaction. Clear? Because we are going to end up with a mixture of close boiling alkanes, which would be difficult to separate. Is this clear? Okay. So that's what we have as the limitation of Wurtz reaction. Okay. Now, that's what we had Wurtz reaction. Now we are going to see. Now this RNA was extremely unstable. Why RNA was extremely unstable was because sodium is extremely electropositive and it puts a very high negative charge on carbon. And that's why this RNA is never isolated. It can be isolated. I'm not saying that it can't be isolated, but it is extremely difficult to isolate and it's going to immediately react with another alkyl halide molecule present in the reaction mixture. Okay. Now, what we do is we can actually make this reaction a little slower and stable. The only thing that we need to do is that instead of sodium, we can use lithium. Yes. So you remember the mechanism of this reaction? So let's leave that then. Very similar. The only thing is that we are going to have RLI plus LIX. Okay, we can have 2Li here. In this 2RLi reacts with CuX to form R2CuLi along with LIX. Clear? Now this R2CuLi is allowed to react with another alkyl halide wherein it gives us RR dash plus RCu plus LIX. Now here we have a slight restriction. This R2, R could be CH3. Hello? Could be 1 degree. Could be 2 degree. Yes. Hello? Could be 3 degree. Could even be benzene. Could even be RC double bond O, that is acyl. That also is allowed. Okay. But this R dash can at the most be CH3 or 1 degree. If you have 2 degree, 3 degree, you are going to get alkene. It would be an elimination reaction. Okay. If you have benzene, then it's no reaction. And if you have RC double bond O, anything, it is a tertiary alcohol. That's how we end up with these different products. So it's not that it's not going to react with anything, but it's going to give a product which is different from the alkane that we are trying to prepare. Okay. Now this is the Corehouse reaction. Okay. Now I have a slight homework for you. I am giving you certain alkanes. Okay. And you have to prepare these alkanes by whichever method you like. You may prepare it by Wurtz coupling. You may prepare it by Corey-House reaction. The only thing that you need to remember is that you are going to use any organic or inorganic compound, but the organic compound must not have more than 4 carbon. Is it clear? The organic compound must not have more than 4 carbon, and you can prepare anything you can take anything else you want. Is it clear? So the compounds that you are supposed to prepare are, first one, this compound, second one, okay, okay. A particular method could be having more than two or more possibilities. Okay. Mm, clear? So these are the 5 things that you are going to do, and we are going to review them tomorrow. I think we have to class tomorrow. No, no, we have the class on Friday now. Can we have the class any day early? Can't can't tolerate it. Nee, I can take, but you won't be able to tolerate it. It yeah, the schools are going on. You said that they're going to be off. Okay, fine. Fine enough. So this is what we are going to do. We are going to discuss it a bit later. Now we are going to get along further. So these are the questions that you are supposed to do. And then we can talk about some other reactions. Now this was the Corey-House reaction. And now we are going to talk about a very important reaction. Now this reaction is called the Grignard reaction. Okay. So when we talk about the Grignard reaction, here we have again an alkyl halide. Now this alkyl halide could be alkyl chloride, bromide or iodide. Of course it can't be alkyl fluoride. Okay. Now this is reactive with magnesium. When it is reactive with magnesium, the solvent turns out to be ether. Now there are 2 different ethers that we use for this particular reaction. One ether is called CH3, CH2, O, CH2, CH3. Now this compound is called diethyl ether. Now this can be written as Et2O also. And it could also be written as CH3, CH2, whole twice O. I'm writing these very formulas because I don't know what form they are going to write it in the exam. They can write it anyway. Okay, and if they are going to write it anyway, then in that case you might get confused. Or they can simply write ether here. Okay, and then there is another ether, which is called THF. Full form, tetrahydrofuran. Tetrahydrofuran. And this, when we talk about this tetrahydrofuran, the structure is CH2, 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 CH2O. This is a cyclic ether. This. The only difference between these two ethers is that if we have any alkyl group, we use Et2O. But if instead of R we have phenyl, we use THF. Okay? So if it is phenyl, we use THF, and if it is alkyl, we use this. Now the mechanism with this reaction is again the same. The only difference is magnesium is a bivalent metal. Being a bivalent metal, magnesium is able to react with the halogen as well as carbon at the same time. So the compound that we end up with is RMgX. Now this RMgX is called the Grignard reagent. Clear? Now if we talk about this Grignard reagent, the electronegativity of carbon is 2.5. Electronegativity of magnesium is 1.2. Okay. The difference between them is 1.3. For a bond to be ionic, the electronegativity difference must be at least 1.7. So this bond is not actually ionic. This RMg bond actually has 37% ionic character. So it is predominantly covalent. There are formulae. By using the electronegativity difference, we can get the percentage of ionic character, and by the percentage ionic character, we can get the electronegativity. That is how they actually were able to calculate the electronegativity. Okay, from the Dipole moment measurements and all. That is how they did it. The electronegativity is not predicted value; it is actually a measured value. Okay. Now, what we find is 37% ionic character doesn't make it actually ionic. Clear? But it is quite ionic compared to other compounds of carbon. Okay. So most often, whenever we have to write the Grignard reagent, we write it as R minus with an electron pair and Mgx plus. So that is how a Grignard reagent is mostly represented as. Okay. Now, in the Grignard reagent, R minus is the unstable species. Okay. And Mgx plus is the stable species. Fine. So, a Grignard reagent will react with any species where R minus can attack. Okay, so just remember, Grignard reagent is a very strong base. Okay, it is a very strong nucleophile. Is it clear? So Grignard reagent is a very strong base. Grignard reagent is a very strong nucleophile. Okay, it is going to react with anything where the the nucleophile can attack, where the base can attack. But of course, it cannot act as a electrophile. Is it clear? Fine. So we are now going to talk about the reactions of Grignard's reagent. Is it clear? Okay. Now I'm going to give you certain reactions. Clear? Let's say we have a Grignard's reagent. Let's have an example. We have CH3, CH2, MgBr, and we react it with carbon dioxide. And then once it has reacted with carbon dioxide, we add HCl to it. Could you give me the product? Mm-hmm. And you add H plus then? Perfect. That's what you get. Okay, fine. The rest of the reaction of the Grignard reagent we are going to do in the next class, which could be on Friday.